Titrations and pH curves. Okay, so we've learned about titrations in the previous class in Chem 1A. So it's just a quick review here. Acid-base titration, we're taking a solution of known concentration, reacting it with a solution of an unknown concentration. Because it's an acid-base titration, one of those solutions is acidic, the other is basic. The known solution could be either the acid or the base, it doesn't matter. As we add the known solution, we're going to monitor the pH either with an indicator, which will change color and tell us when we get to the end, or with a pH meter. At the equivalence point, we have added, according to the stoichiometry of the particular acid and base we're using, we've added a stoichiometric number of moles of acid equal to the number of moles of base. So the moles of acid and the moles of base completely balance out and react, and at that point we say that titration is complete. And from the volume of the known solution, we can calculate the concentration of the unknown solution. So that's the big idea of titration. And now we're going to look at the minutiae of titration. Well, after this slide. Pictures. Pictures are nice. So, here's the beginning of the titration. You've got acid in here and base up here, and you're going to add this. And at first it seems that nothing is happening, and then we start to see a little pink. This is a phenolphthalein indicator. As it gets to a basic solution, it's going to turn pink. So as we add more, the base and the acid are reacting in here, neutralizing and forming water. And when we get just a teeny tiny bit past the equivalence point, the little bit of excess sodium hydroxide causes it to turn pink, and we know we should stop now. Okay, so that's all stuff you've learned before. So we're going to go into a little more detail. We're going to talk about titration curves or pH curves, two different names for the same thing. A plot of the pH of the solution versus the volume of known solution that has been added. You did a titration like this in that 3-day lab that you did while I was sick. So this is one of the reasons why I wanted to delay the due date for that, is so that we could cover this a little bit, and then the lab would make more sense. Okay? So this is an example of a titration curve. This one is representing 50 milliliters of 0.1 molar HCl being titrated with 0.1 molar sodium hydroxide. And what we see is that the pH inches up until we get close to the equivalence point, then it shoots up very quickly, big change here, and then it levels off again. And the point of inflection is where this is a curve, depending on which side you're looking at it, concave or convex. And at some point right here, it switches to going the other way. That's the point of inflection. That's the equivalence point. And near this equivalence point, the pH changes a lot with a small amount of base that's added. Now, the exact shape of this is going to depend on a lot of different factors, whether you're titrating a base with an acid or vice versa, and also, is it a weak acid or a strong acid, or exactly which acid you have.
You mean it can be more flat, or what do you mean by change?
Well, if we titrate sodium hydroxide with HCl, it's going to start up here and then come down that way. So it'll be like backwards. But the shape can be different, and the equivalence point, this equivalence point is at 7. The equivalence point could be above or below 7. And this could be really steep, or it might be not quite as steep.
So the change between the bottom and the top of the straight part is very, very small. How do we know exactly where the equivalence point is? Is that a calculation?
There's different ways to determine where that point is. Yeah. So let's look at a specific example. 25 milliliters of 0.1 molar HCl, and we're titrating it with 0.1 molar sodium hydroxide. This is a strong acid with a strong base. So first, let's find what's the volume of sodium hydroxide that's required to reach the equivalence point. Well, there's different ways to calculate this. And I know that some people like to use the dilution equation, M1V1 equals M2V2. The really dangerous thing about that is it works sometimes, but not all the time. I prefer to go with things that work all the time. And so I prefer to view titration as a stoichiometry problem. And that, I think, gives you a better understanding of what's going on instead of blindly plugging numbers into an equation. So here we've got 25 milliliters of 0.1 molar sodium, that's not sodium hydroxide, hydrochloric acid. So some of you have taken 1A with me, and you know that we chant grams to moles to moles to grams. That's the mantra of stoichiometry. And then we just mix it up a little bit. Sometimes we start with milliliters and go to molarity or something. We just switch up the ends, but in the middle is always moles to moles. And in this equation, this is a nice simple one. It's a mole ratio of 1 to 1. But basically what we're going to do is we're going to start with what we know. We've got this volume, molarity. Remember that capital M means moles per liter. That's a conversion factor most of the time. So 25 milliliters of HCl, and we want to convert that into moles. Most of the other instructors here use millimoles, so I'm going to use millimoles. So 0.100. Now, if you haven't used millimoles before, this is how it works. That's 0.1 moles per liter, right? If I put milli on the top and on the bottom, does that change it? No. So I'm just going to stick a milli here and a milli there. Those, we could cancel those out and get rid of them if we wanted to, right? Yeah. But what's nice about that is you see the canceling working out so much sooner. So that's millimoles of HCl. And they actually have a stuffed millimole. She's really cute. I'll have to find her one of these days. And then we have 1 millimole of sodium hydroxide to 1 millimole, forgot the M. No. Yes. Brain dead. HCl, and those cancel out. And then, what's the concentration? It's 0.1, right? What are we trying to find? We're trying to find a volume. So we're going to have milliliters up here and millimoles down here. So that's 0.1 millimoles per milliliter. And those units cancel out. And we end up with 25. Which some of you look at that and we're like, well, duh. But that's the process of writing it out. Once you get that process of writing something out like that firmly in place, then you can start to do some things in your head. So, 25 milliliters. The concentrations of acid and base are equal, and so the volumes are going to end up being equal. Now, what is the pH before we add any sodium hydroxide? Well, this is a strong acid, right? HCl dissociates, ionizes completely. So the hydrogen ion concentration is going to be the same as the concentration of the acid, 0.100. And so then what's the pH? The pH is going to be the negative log of 0.1, which is going to be 1. I should have 3 zeros. So the pH is 1. And so then on our titration curve here, for 0 volume of sodium hydroxide added, we have 1.1. What about after we add 5 milliliters of sodium hydroxide? Okay, so they made a chart here. So before the addition, we had no sodium hydroxide, and we had 0.00250 moles of hydronium ion. Where did that come from? It comes from the concentration, it comes from taking the volume times the concentration. That's where they get the 0.0025. So the volume of the acid times its concentration, you figure out the number of moles. So that's the moles of acid. It all ionizes into hydronium ion, so that's the initial. And now we're adding 5 milliliters of the sodium hydroxide. So you do the same calculation, but it's 0.005 liters times 0.1, and so that's where they get this number. We're going to assume that it all is going to react. So all of that reacts, and so we end up with 0.0020 moles of hydronium ion. That's the number of moles. The tricky thing about titrations is the volume of the solution is constantly changing. And so that's why we had to do this in moles. And now the total volume is the initial volume plus the volume of sodium hydroxide that got added. And so then we can calculate the new concentration of hydronium ion, and then we can do the pH, right? So that's negative base 10 log of 0.0667. So pH is 1.76. Any questions? What about after we add 10 and 15 and 20 milliliters of sodium hydroxide? It's the same calculation that we just did. It's just a little change every time. So you take this volume combined with that molarity to calculate the number of moles of sodium hydroxide that were added, and you see how that reacts with the number of moles of HCl that were initially present. You find the number of moles of hydronium ion that are present now, and you divide by the new volume. And so it's just tedious is all that it is. It's tedious. And so there's a space there, but I'm not going to do all these stupid calculations. So these are the results. 1.37, 1.60, 1.95. So we graph those. Any questions?
Why are we doing this?
Why are we doing this?
There's got to be more common sense to why this.
Well, normally we don't do the calculation. Normally we measure the pH. But we have to go through this agony so that we can understand what's going on. Well, how about after adding 25 milliliters of sodium hydroxide? This is the equivalence point. We figured that out earlier. 25 milliliters will be the equivalence point. So, I don't know what's wrong with me. Okay. I need a vacation. That's what's wrong with me. But it's not a vacation.
Chance to catch up.
Mothers just don't really get vacations. Okay. So we initially had 0.0025 moles of acid, right? and now we've added 0.0025 moles of base, right? So those are going to react completely, and we're going to have no acid and no base left. And so what's the pH going to be? It's going to be 7, because there's the autoionization of water, right? The hydrogen ion concentration times the hydroxide ion concentration equals 10 to the minus 14. And here what we have determined is that these are now equal. And so the hydrogen ion concentration is going to be 10 to the minus 7, which gives us a pH of 7. And that's where this point comes from. So at the equivalence point, titration of a strong acid and strong base is going to be 7. Question?
So how can you have ones that where it's not, right? So
When you have a weak acid or a weak base, then the pH will not be 7. Yeah. And see, after we go through this whole calculation thing, we're going to do it again with a weak acid. But I don't think we're going to do it again tonight. I think we'll give ourselves the weekend to recover. So we'll just look at this one for now. Well, what about going past the equivalence point? What's happening now? Well, is it time to go home yet? Yes, it is. It really is. So we started out with 0.0025 moles of that and basically none of this. And now we've added, at 35, we've added 0.0035 moles of that. And so this is going to react with all of that, right? And so we're going to have none of that left, and we're going to have 0.0010 of that left. And so we can calculate the pH of that, which that doesn't look right. Did I do something wrong? I probably did. Because the pOH would be 3. And then the pH should be 11, but it isn't. What did I do? I'll pause. Okay, I forgot about the ever-changing volume. So this is 0.001 moles of hydroxide ion remaining. But now what's the volume? It's the original 25 or 0.025 liters plus the 0.035 liters of sodium hydroxide that we have added. So it's 0.001 divided by the sum of 0.025 plus 0.035, which is 0.01667. That's the hydroxide ion concentration. This is all getting extremely sketchy, I'm sorry. So negative log of that, the pOH is 1, that's not pOH. pOH is 1.778. The pH equals 14 minus that. And that's where we get this guy, right here. So, do as I say and not as I do. Don't forget the changing volume. Right? So here's the overall pH curve. The initial pH calculated on the concentration of the acid before we've added anything. And then we have this This part here, this is all going to be acidic pHs because we've got more acid than base. At the equivalence point, we have equal amounts, and for a strong acid and a strong base, the pH will be 7. And then afterwards, we've got excess hydroxide, excess base, and so the pH is higher. Any questions? What if we titrate a strong base with a strong acid? Well, it's really similar, just kind of opposite. We start with a basic solution, and the pH drops. At the equivalence point, it's still going to be 7, and it drops to acidic as we add excess acid. And so, of course, you could do the same sorts of calculations. Okay, so we'll do this one example, and then we'll call it a night. So a 50 milliliter sample of 0.2 molar sodium hydroxide is titrated with 0.2 molar nitric acid. Calculate the pH after the addition of 60 milliliters of nitric acid. No, this isn't so bad. And this is the sort of problem that you would normally be asked, not calculate the whole stinking pH curve, but just do one. Do 1 point on it. Okay, so this is how I think about these things. So we've got sodium hydroxide plus nitric acid, and that's going to neutralize and form sodium nitrate and water. And we really don't care what the products are, but we do have to have our stoichiometry straight. This is just 1 hydroxide per mole, and this is a monoprotic acid, so it is 1-to-1. And then I like to use that chemical equation to help me organize my information. So 50 milliliters of this. So I'm going to write those numbers under the sodium hydroxide. 50 milliliters, and that's 0.200 moles per liter. And then it says we're titrating it with 0.200 moles per liter nitric acid. And it says we've added 60 milliliters. Of the nitric acid. It's asking us to find the pH. This is a strong base and a strong acid. So the amount of hydroxide in the solution is this volume times this concentration. So let's figure that out. I'm going to use millimoles because I just think it's easier here. So we've got 50 milliliters times 0.200 millimoles per milliliter. So 50 times 0.2. You know, we should be able to do that in our heads, but, better safe than sorry. And I'm going to preserve my sig figs, and that's 10 millimoles of sodium hydroxide. And then over here, I've got 60 milliliters times 0.200 millimoles per milliliter. So 60 times 0.2 is 12. 12.0 millimoles. So I've got that much acid, and I've got this much base. They're going to react, right? Which is there more of? There's more acid. So after this reacts, what am I left with?
2 millimoles.
I'm left with 2 millimoles of H+. Okay, so then I need a concentration though, right? I'm running out of space because I am not planning ahead well. So I'm going to switch colors so that maybe it won't be as confusing. 2 millimoles of H plus, what's the volume? 50 plus 60, 110 milliliters. Now the milliliters cancel out and I get back to molarity. 0.2, not 0.2. 2 divided by 110. And that's one of those fun numbers. 0.018. Repeating. And that's molarity
Of H plus.
of H plus. So I can use that to calculate the pH, which I'm going to do over in the other little corner that I've left. The negative log of 0.181818. Yes, 0. I've made a habit of leaving out those zeros tonight. Those are important. How many significant figures does that concentration have?
3?
Only 2, because look what happened here. Where did that 0 come from?
No idea.
It shouldn't be there. Go away. So this is just 2 sig figs, but I'm going to go ahead and use that whole number. It's in my calculator, I might as well, right? Negative log, maybe better make it the base 10 log, that always helps, of that guy.
Natural log.
Yeah, I don't want to use the natural log. And so I get a pH, 2 sig figs, 1 point, it's not even a very good one, 1.74.
It's pretty acidic.
That is pretty acidic. Any questions? Yes, we can go home now. We will talk about weak acids on Monday. Something to look forward to.